afternoon, or good evening to those of you in Europe, and apologies to those of you in Australia and China. Welcome to Session 10 of the ESIG 2020 Fall Technical Workshop, being held online on Tuesdays and Thursdays during the month of October and into early November. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As with so many things we were planning to do in person this year, our plans were derailed by the coronavirus, and here we are online again. The workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoiva-san of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who make ESIG what it is, and we encourage you to become involved if you're not already. Regarding logistics, I would like to ask you to note that the webinar will be an hour long. We will have 3 individual presentations of approximately 12 minutes each, and we plan to hold the questions for a 15-minute Q&A session after the last speaker. As we're doing with all of our webinars now, we'll be using the Slido platform for managing the Q&A. We would ask you to use Slido for your questions, as you will not be able to ask your questions through WebEx. You should go to slido.com on your device and enter ESIG29, ESIG29, as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also in the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. And I'll guarantee you that your votes will be counted. So please keep the questions coming during the presentations, and we'll address them at the end. Recognizing the limitations of a webinar with typically more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG29 as the event code. Session 10 today deals with a very timely topic, offshore wind developments. Offshore wind is a quickly moving area, due in large part to the progress made in Europe and the resulting rapid decline in cost of energy. Offshore wind energy doesn't do much good unless we can move it onshore, so that's our topic for today, wrapping up a very busy week for offshore wind in the U.S. Today's session will be chaired by Fara Courtney with Outer Harbor Consulting. Melinda Marquis with NREL will be serving as co-chair. Fara is a principal consultant with Outer Harbor, providing consulting services to a range of domestic clients. Melinda is the offshore wind grid integration lead at NREL. I've had the good fortune to work with both Fara and Melinda previously, and both are active participants in ESIG. We look forward to their continued participation. Fara and Melinda, we appreciate having you here, and I'll now turn it over to you, Fara.
Thank you, Charlie, and hi, everyone, and thanks to all of you for listening in. Like Charlie said, this was a big week for offshore wind transmission specifically. On Monday, the Business Network for Offshore Wind issued a white paper on transmission that makes a compelling case for new thinking on interconnecting offshore wind power into the East Coast markets. And on Tuesday, FERC held the first day-long technical workshop focusing specifically on ways the transmission planning process might adapt to better respond to the public policy needs of coastal states with a big offshore wind ambition. So this panel makes a great finale to the week. I want to welcome all our panelists and introduce our first speaker. Pfeifenberger is principal at the Brattle Group. He's an economist with a background in electrical engineering and over 25 years of experience in wholesale power market design, renewable energy, electricity storage, and transmission. Most recently, Hannes evaluated offshore wind transmission options in New York State and New England, and the presentation today will focus primarily on the New England case study. Hannes?
Thank you, Sarah. I hope everyone can hear me, and it's really nice to be here. Thank you for the invitation. Let's see if I can manage the slides. As Farah said, we have done quite a bit of offshore wind transmission discussions here in the U.S. over the last couple of years with a technical conference just a couple of days ago at FERC. Many of us have seen each other there, so I'm glad I can talk to you. This is work we have done for Untitled, which is an independent transmission developer. And the question that we had been asked is, what is the difference between the current approach of sort of one offshore wind generation projects with a gen-tie onshore versus a more planned approach to a onshore-offshore optimal grid solution? And the motivation for that is really that offshore wind is on the table here in the Northeast, particularly as one of the most abundant and fairly cost-effective clean energy solutions. As you may know, the northeastern states along the Atlantic coast, so not just New England, New York, but also mid-Atlantic, run by PJM, New Jersey in particular, have very ambitious clean energy goals over the next 10, 20, 30 years. And there's a lot of commitment for offshore wind. Currently, the eastern U.S. states have committed in total about 30,000 megawatts of offshore wind, of which about half are in New York and New England. And what this table shows you is that New England has already contracted 3,000 megawatts, New York about 1,800 megawatts. There are solicitations going on right now for another 3,000 to 4,000 megawatts, and the total commitments through about 2035 or so in New England and New York, almost 15,000 megawatts, as you see here. But the states have much bigger goals than that, with an 80% economy-wide decarbonization in both New England and New York. A lot more clean energy will be needed, and how much that will be is still being analyzed, but the number of studies have shown that just the offshore wind need for New England might range from 25,000 to 40,000 megawatts by 2050, and between 15 and 25,000 megawatts by 2040. Now, how one would integrate that much offshore wind into the local power markets is, of course, a real challenge, and that's why the question of should one keep doing this one generation interconnection project at a time or plan a more optimized grid is of real importance. The speed by which renewables will have to be integrated is also unprecedented. This is a slide from a study done by my colleagues that shows, depending on scenario, New England alone will have to integrate between 3,500 and 77,000 megawatts each year over the next 30 years to achieve the 2050 economy-wide decarbonization goals. What you see here on the left is historically, even now where we are at a time that already feels ambitious, we have not been integrating in New England more than 1,000 megawatts a year. So we are really talking about annual renewable generation additions that are about at least 5 times higher than what the region is used to today. So I've talked about this a little bit. We've done 2 studies for America, one for New England, one for New York. This slide presentation is mostly focused on the New England work, but the results and approach is very similar. The idea is really that, and maybe I can move on here, that we have about 14,000 megawatts of offshore wind lease areas already designed or specified just south of New England, 15 miles south of Martha's Vineyard. And what you can see here, the New England states have contracted 3,100 megawatts already. They have already committed to another 3,600 megawatts. And to fill just the New England lease areas for offshore wind that BOEM has specified, New England might really be able to get about 8,500 megawatts from those lease areas, with some of the capacity being shipped over to New York. So we looked at this phase 2 current commitments and phase 2 to sell the rest of the currently specified lease areas. And under a Gentai approach, the situation today has been that these wind farms have been in the 400 to 800 megawatt range. At that size, at that scale, you would typically use AC cables with about 400 megawatts each. So to get 3,000 megawatts of additional offshore wind into New England, you would need about 9 individual 400 megawatt cables. With the Gentai approach, we have assumed that the generators would tend to choose the closest onshore landing points that are, reasonably robust, whereas a planned approach would actually look forward and choose landing points such as Bridgeport and Boston that are considerably further away at considerably higher cost for individual Gentais. So these Gentais, while cost-effective from a long-term planning perspective, might not come about from individual bids because this generator might not be cost competitive if they bid a Gentai into Mystic and have to compete with a generator like here, who just goes into a closer by point. Moreover, HVDC lines that the planned approach would be using are more expensive than AC lines. But the interesting difference between these two figures that is even more pronounced if we integrate all of the lease areas of about 85,000 megawatts is that the unplanned approach of one generator at a time creates a lot more onshore transmission congestion, onshore reliability violations, and the need for large onshore upgrades that you see here on the left. While the planned approach with HVDC technology and interconnecting the offshore wind areas to more robust and more optimal interconnection points that avoid these onshore grid upgrades. With those better interconnection points, you avoid these onshore upgrades. And what that all means is the difference between a generator lead line and the more optimized offshore network approach is that while, as you can see here, the offshore transmission cost is about 20% higher under the planned approach, the onshore upgrade costs are about 65% lower, with the total impact that the transmission solution is about 10% lower under the planned approach. Now, you may not ever get there with an unplanned approach because each generator, some of these benefits that you see from the planned approach are really socialized across the entire system and cannot be captured by individual generators preparing their bids. You also see that HVDC technology, while more expensive, has fewer losses. So we have about 40% lower losses under the planned approach. We have about half the marine cable mileage because the HVDC technologies are using fewer cables, even though they reach more distant landing points. Being able to inject power into Boston as opposed to near the coastline also gives you more value and the customer benefit of getting the offshore wind energy to more valuable parts of the grid. We see more competition. Europe has shown that bids at offshore interconnection points are much more competitive than bids who need to arrange for their own transmission. And of course, fewer landing points means fewer environmental impacts, better utilization of the lease areas, and more competition in general. It also allows third parties to buy smaller shares of the system. So you don't need to have a bid fit an entire generator lead line, but you might be able to have Google or Microsoft or other industrial customers, hospitals, universities, buy, say, 20 megawatts of offshore wind at a time. Whereas the generator lead line approach pretty much requires a bid to be large enough to fit into an individual gen tie. This just gives an example of the kind of onshore overloads that you get if you don't plan the offshore grid correctly or optimally. And you can imagine that making these onshore upgrades is not only costly, but permitting them is a real challenge. And there's a real risk that you can't even permit some of these onshore upgrades, or that the onshore upgrades would be delayed considerably due to permitting challenges. But what we found in this study was that through an unplanned approach, the next 3,600 megawatts might trigger about $1.7 billion in onshore transmission upgrades. And that need for upgrades can largely be avoided by choosing more appropriate interconnection points or more favorable interconnection points, such as in the Boston area rather than down directly near the coastline. Here's just a summary of these results. In an unplanned approach, you end up with total transmission costs of about $4.4 billion. With a planned approach, you spend more on offshore grid, but much less on onshore grid, with overall cost savings that get to be about $3.9 billion. Of course, there's a lot of uncertainty, but the uncertainty is not just about cost, but also about constructability. One unique situation that pops up quite frequently is that some of these interconnection points cannot accommodate many cables. Brayton Point is a retired coal plant, could accommodate 1,600 megawatts, but there's a very narrow channel that only has the spacing for 2 cables. If you put 2 AC cables in there, you can only interconnect 800 megawatts, even though you could do it much better than that. With DC, you can easily get to 1,200 megawatts, so you can actually use the interconnection capability of that retired coal plant much more fully with a planned approach, or a gen tie that uses HVDC technology, which is in part why the next round of solicitations by Massachusetts and New York have scaled up the size to at least 1,200 megawatts to allow for these technology options. Cable mileage, fewer cables means less marine trenching. Just to step back, this kind of planned approach, of course, is being used in Europe now, but we also have been using that for onshore wind in the US, not just in Texas, as this example shows, but also in California, in the Midwest. So a planned
I'm afraid we're going to have to wrap up soon. So if you could just make a closing point so we can move on to the next speaker, that would be great. I know you have a lot more to say, and hopefully we can get to some additional points during the question.
Yes, I am pretty much done. The idea of how to make this work is that you have a separate solicitation for the transmission network. And if you do that, of course, you have to think about how to mitigate the project and project risk. But maybe we won't go into this, and I hand it back to you, Fara. Thank you for the reminder, and thank you for listening.
Thank you very much, Hannes. You did a great job of laying out the challenge and the opportunity that we have to think differently about offshore wind transmission. Next up, we have Michael Goggin, Vice President at Grid Strategies, LLC, a consulting firm focused on grid and market issues for clients in the clean energy industry. Michael formerly worked with the American Wind Energy Association on transmission policy, and he's one of the authors of the just released white paper on offshore wind transmission that I mentioned in the beginning. Michael?
Yeah, thanks a lot, Fara. And yeah, for folks who want to check out that white paper, it's a longer version of what I'm going to say, and it was also included in the FERC technical conference. I used that as my kind of written submission. So check out that document, and then there's a recording of what I said on Tuesday, as well as what Hannes said on Tuesday at the FERC conference. I think we covered a lot of these issues in probably way more depth than most people would care, but check that out if you want it. So I'm going to talk about the policy side, particularly transition planning and cost allocation, and how we can get a workable policy that will allow offshore transition as well as the onshore transition upgrades that are needed to be built and allow that to happen in the most efficient way possible. And the key to doing that is, and this is informed by the success we've had in regions like Texas with CREZ, as Hannes mentioned, and then particularly I think the example of MISO, the multi-value projects, is really, I think, one of the best illustrations of what we need to be doing. And with the MISO multi-value projects, again, one of the key things is that they're multi-value. And what I mean by that is that too often the way most of the RTOs look at transition planning is they put transition projects into buckets. They'll say, okay, this is an economic project. It's used to reduce congestion on the grid. Or this is a reliability transmission project. We need it to meet NERC criteria or replace an aging line. Or this is a generator interconnection project. And that's typically how most of the offshore upgrades that are, the offshore wind projects are coming through, and how the upgrades are going to be built is kind of in that generator interconnection process. Then there's public policy, which is often similar to the generator interconnection. The problem with doing those in buckets is that you miss the ability to optimize across all of those categories of benefits and to find often a different configuration that would, for example, interconnect the generators you're trying to, but if you build it in a certain way, you can also reduce congestion on the grid and help meet some of the reliability needs. And that's what the MISO portfolio that they put forward and that's now being built out did. It kind of achieved all of those benefits in an optimal way. It built a portfolio of projects across the entire region and showed that they had a benefit to cost ratio of about 3 to 1. Those benefits are broadly spread across the region. And that allowed them to then do the critical piece, which is pairing it with the cost allocation or the paying piece, and basically demonstrate that the entire region should broadly pay through just ratepayer funding, pay for the transmission. And that's the key issue. And the cost allocation is really the hard nut to crack here. Planning, anybody can draw lines on a map and make it work. The hard piece is getting people to pay for it. And the problem in our planning process is we put those projects into buckets because the planning is tied to the cost allocation. Those projects go into those buckets because that determines how the cost gets paid. The generator upgrade, interconnection costs, those projects, the cost of that goes to the generator. Reliability goes to the local area, economic, there's a complex formula. And that basically, the cost allocation drives the inefficiencies of the planning process. And so the key thing is to you have to solve these problems together with a proactive planning approach that then is coupled with a broad cost allocation. And we can see that the failures of the current process in the generator interconnection process, basically what's called participant funding. We're requiring interconnecting generators to pay essentially the full freight of all the upgrades that adding their generator will cause to the system. And for the offshore projects that have been proposed, in many cases, these are billion-dollar upgrades. You're rebuilding large sections of the onshore transmission system, 345 kilovolt, 500 kilovolt, massive new transmission lines. And it's kind of, it's unworkable to expect interconnecting generators to pay for those network elements. that are providing benefits to the entire region. And this is kind of the classic free rider problem that affects transmission, is that, and which is why we need broad cost allocation, is that as an interconnecting generator, I have little incentive to pay for something that's going to benefit the entire region and my competitors and other forms of energy. And so it really is just, it's not workable to have the interconnecting generator paying for these projects. And as a result, we see this large queue backlog. This is what's been the bane of onshore wind for the last decade or more. Is now there's a large interconnection queue backlog for offshore wind, and many projects are balking at these $1 billion upgrade costs. And again, this cost allocation needs to be fixed. So, and I think the proactive piece, the two elements of the planning are the multi-value, looking across the benefits of transmission, economic reliability, and generator connection, but then also doing it proactively. And that proactive thing is actually quite easy with offshore wind. With the land-based wind, it was some of a challenge with CREZ, with the Argos study and MISO that predated the MVPs. We kind of, people had to go out and look at the interconnection queue, look at where the wind resources were, and kind of say, okay, if we build the transmission, they will come. And luckily they did. These were good wind resource areas, and the generation did come after the transmission was completed. There's not that risk with the offshore wind. These are being driven by state mandates. They have very precise quantities in certain years that are going to be deployed. We know where the lease areas are, so we know when and where and how much of the transmission and the generation is needed. And so the proactive planning is easier. The politics of getting the multi-value planning and the broad cost allocation still challenging here. And I think that's exacerbated by the fact that this is kind of where most of the offshore lease areas kind of at the seam between three RTOs, and there's currently no workable mechanism for dealing with those inter-RTO benefits and allocating costs. Hannes covered a lot of this stuff. Basically, a planned approach is just far superior to an unplanned approach. Just to drive home that this has worked. I think about half the wind, the land-based wind that's been deployed in the U.S. has been the result of successful transmission policies, particularly the CREZ in Texas, the MVPs in MISO. SVP had a similar approach through their highway-byway cost allocation. And this has really, I think, gotten the U.S. wind industry to where it is. And we know it works, and we need to do it for offshore wind. Again, it's the proactive multi-value planning with broad beneficiary-based cost allocation. So one of the big conclusions of our paper is we laid out a few tables. There's a table at the end that goes through different options for how to do planning and cost allocation for transmission. And so the first one is kind of the status quo. This is basically the generator lead line. So, the generation developer who's developing the offshore project also develops the transmission project. They plug in typically at the closest point on the grid. And, that has advantages. It's easy, it's controllable. There's less risk. The disadvantages are you're going to, as Hannes was explaining, you can inefficiently use up some of the good interconnection points on the onshore grid, and you're going to end up over the long term incurring more onshore upgrade costs as you have to kind of rebuild the onshore power system to bring in power at less optimal places. So, it's going to happen. Certainly, this first tranche of offshore projects are all going under this first generator lead line model, and that I think just the timelines involved, that has to be how that's going. But in parallel with that, I think we need to be thinking about what the long-term solution is. Can we do this better so that for some of these later projects, as we get these much higher targets, gigawatts, many dozens of gigawatts over the next decade or two, that we have a better policy in place. And so number two is what I've outlined, kind of the proactive planning with the broad cost allocation. This is kind of the ideal. It's what's worked. So it is politically challenging. And so it's presented as an ideal here. And then I think most of the rest of these options are kind of hybrids of, if we can't achieve that ideal, what can we do to get closer to it? So option 3 is one of those where this was done in California for the Tehachapi wind resource area back about 2006. FERC endorsed the policy that was brought forward by the California grid operator to basically upfront, the grid operator would use ratepayer funds to upfront kind of pay for this transmission upgrade. That was a network element, so it was interconnecting generators, but it was also serving economic and reliability needs. they would pay for it up front, but then as the wind generators interconnected over time, they would pay in kind of cost share for the transmission. So it's kind of a hybrid. There's not a total broad regional cost allocation over time. And so I think this has some advantages and could be kind of a compromise approach. There's also a model that FERC has created that's never been used by a project, but I think it certainly would work. The anchor tenant model, which is basically a large single customer, and this works particularly well with DC lines. A large single customer, the offshore project, comes in and subscribes most of the capacity on the line. They do that at negotiated rates. And this is kind of an exemption to FERC open access provisions that require market-based kind of competitive transmission rates. You can have this anchor tenant that gets kind of an extension to that process. And that gives you the certainty that allows the project to go forward, and then you use the market-based rates to kind of sell the rest of the capacity on the line. So this could, I think, particularly for the offshore pieces of the grid, I think could have value. Obviously, the land-based stuff, it's going to be probably mostly alternating current. This probably would work less well for that. And then number 5, as I was kind of mentioning, this is kind of a hybrid of those two, where you have the broad regional cost allocation with proactive planning for the onshore piece, but you use something like the merchant transmission potentially with this anchor tenant model for the offshore piece because it works better there with the DC lines. Number 6 is kind of probably even farther into the future and even more idealistic is not just having within the region, within the RTOs, having a good planning and cost allocation, but expanding that interregionally between the RTOs. And obviously the free rider problems and just getting the political interests aligned is even more challenging across 3 RTOs or 2 RTOs than it is within an RTO. So it's held out there as an ideal. I think that certainly, this would be the economic optimum to kind of, particularly where we're looking at, this is a very congested part of the U.S. grid, the Northeast corridor. There's a lot of dependence on gas generation. There's a shortage of pipeline capacity. We've seen during events like the bomb cyclone, polar vortex, you have extremely high prices. You even have reliability, resilience risks, and having an offshore network could be extremely valuable. But it is politically challenging to get that done. But I think that should be the ideal, is kind of the same policies we're doing at the regional level, at the interregional level. And then a few ideas to kind of maybe that could be some kind of compromise. I think there could be interest, depending on what happens in our election next week, there could be interest at the federal level in using federal dollars, either through grants, tax credits, loan guarantees, something like that, to kind of reduce the cost of capital and give a some cost share for an offshore grid. I think it makes sense. There's a history of the federal investment in transmission, and particularly given the large benefits for the entire eastern U.S., I think this could have value. And then there's also, so that I think could be a part of the solution. This last one is not really an ideal solution. It's kind of a part of the existing policy of kind of states could kind of work together. You're never going to get the efficiencies that you would have by looking across the entire region. So I present that as kind of a, it might be an option, but it's certainly not an ideal option. Ideally, you want to be looking regionally and looking at all of these benefits. So that's all I had. I look forward to the Q&A. Thank you.
Thank you very much, Michael. Lots of good options on the table, and it's really good to hear about success stories in other parts of the renewable energy industry, other parts of the country, solving these kinds of transmission questions. Our final speaker gives us a view from Europe. Peter Markussen is head of Energinet, managing the international consultancy activities using the Danish experience to increase the global use of renewable energy. Peter will be sharing some of the latest thinking from Europe about offshore wind and hydrogen hubs. Peter?
Thank you. Thank you for the introduction, and thank you for the invitation to say a few words about the European setup here today. I work for Energinet. It's the Danish transmission system operator, and we operate and develop the transmission and both for electricity and gas in Denmark. And we also have the system operation responsibility, so we ensure the balance on day-to-day, but also long-term. And we are owned by the Danish Ministry of Climate, Energy, and Utilities, so we are also a non-profit organization. our vision is green energy for a better world. Just as a few facts on the Danish energy system. Today we have around 50% of wind and solar, and we have a target of 100% green electricity in 2030. So we are quite ambitious here, and there is a lot of development going on at the moment with both onshore wind and solar, but also offshore wind. And we have a target of 100% green energy in the system in 2050. And then also we would like to reduce CO2 with 70% compared to 1990 in 2030. So there is a quite ambitious political target. So when we look at offshore wind, we look at it from a Danish, but also from a North Sea perspective. We are quite integrated in the North European electricity system. Today there is around 20 gigawatt, and we are moving towards almost 70 gigawatt in 2030. Of course, there are some challenges here. One is on geography. There is a quite long distance from some of the offshore wind farms to consumption. There's also the challenge with simultaneity, that wind is not always producing when there is a consumption. So we need to have some kind of flexibility in our system. And there is the predictability. There are uncertainty and complexity both in the planning, but also in the operation of the system. And then finally, we also see an accelerated development where new technologies are moving on very fast. For example, batteries and also solar is getting much cheaper. And also the way of using electricity is changing. And we also see digitalization with new business models, new companies trying to be part of the energy sector. So that's all in all make it quite complex. But we expect that offshore wind will add up around 20 to 40% of our electricity consumption in the future. And on the grid, you say this, we are quite integrated. In Denmark, we have quite strong grid, also the same in Holland, whereas, for example, in Germany, there are some challenges. It can be maybe compared to some of the US situation, and there is a need for development and in general, long-term planning. So what do we do when we look towards 2030? One thing is we have started cooperation with the German and Dutch TSOs as well, looking at the North Sea as a hub, and not just as different points where you could put up offshore wind, but try to see how we can combine it. So it's international cooperation where we look at common planning, common regulation, contracts that might be necessary, looking at different ways of cooperating also with the gas system, Gas Unie, the Dutch gas TSO is part of it as well, and also with some of the ports in the North Sea area. Then we also look at energy islands to have large-scale solution when we are quite far away from the shore. We need to see how to reduce costs so it will not be too expensive. One possibility is energy islands. In a start, it will probably be connection just to one country, but it could also be to more countries. That's something we are looking at. And actually, the Danish government has decided that we should have an energy island in 2030. So we are moving on quite fast here to find out how to do it and who should actually build it. Is it infrastructure or is it part of the commercial tender? Then we also need flexibility in the system, and here sector coupling is the main answer from our side, so that we can increase the value from the electricity. Otherwise, if you just have a lot of electricity from wind in the system, the electricity price can be very low. But we need to create value and use the electricity as clever as possible. And that's where we also look at hydrogen hubs. That's a way of getting renewable energy from wind to, for example, the transport sector, and also to processing industry. But first, a few words about our experience. we have a number of offshore wind farms started already back in 1990 with some of the first small wind farms, and now they're getting much larger. Most of it was as a generator tie line direct to one price area. But we have actually now also developed Kriegers Flak between Denmark and Germany, where you have a backbone coupling more offshore wind farms and the multi-state. And at the same time, it's also two synchronous areas where we then have a back-to-back converter in Germany so that we can synchronize between the two countries. So the connection actually works also as an interconnector between the two countries and not just as transport of offshore wind. And then we're looking at the energy island as a kind of a hub. The first one will be a single state, but in the future we see that it will be multi-stated. And of course there is a need for planning to be able to do that. Maybe a few words on the grid in Denmark. The grid is financed on the tariff by the consumer, but the connection is paid by the consumer or producers to the nearest connection point. But when we look at offshore wind, we have built it all the connections until now. But for the next tender, it will be part of the tender also to build the connection to onshore. Of course, it costs money to develop offshore wind, and it also influences our tariff paid by the consumer. But on the other hand, they actually also have a lower price today than they had historically. So all in all, we look into a stable price. Maybe from hour to hour it will be very volatile, but in general it will be quite stable. But there is also a demand for flexibility on the consumption side. And when we look at consumption, we look at we say both sector coupling with the heating sector. We have a quite large grid of distributed heating. We look at transport, we look at industry, and then we also look at more indirect electrification, power to X, where you can transform the electricity into molecules and use them in, for example, heavy transport, refineries, ammonia, steel, sea transport, air transport. But that is when we look towards 2050. But already now we have more projects going on for power to X. And our role in it is, say, as responsible for the infrastructure, where the green arrows, that's the private initiative, the commercial partners, and then the dark green ones, that's the infrastructure part. And here, of course, we can use our advantage being both the gas and the electricity TSO and try to combine it and see how can we use the gas grid, the grid, or the pipelines for gas, but also storage possibilities. Where we today have natural gas, maybe it could also be used for other kinds of gases. So here there is a large setup being developed for doing this. And we of course do some grid planning, and what we can see is that currently around 4 to 6 gigawatt of the offshore wind that will be built for the next 10 years in the North Sea will be able to be integrated in the existing grid. But as you saw, the ambitions are quite higher. So we also look into develop feed-in zones where they can set up your electrolysis for producing hydrogen or the transformation to other kinds of gases or liquids. So there we look at towards 2030 of a potential between 1 to 3 gigawatts, and are now looking at the map to see where would it make sense to have feed-in zones. But there are discussions going on also with the commercial developers that would like to have an influence on where to locate it, and also would like to be more free to locate it where they, for example, have their industrial production already, or they have refineries. So there is a discussion going on today, and trying to have a transparent planning process as possible, because everybody in the discussion knows that if this should succeed, we have to keep costs as low as possible, and here planning is quite important. And then just as a last slide, we see Denmark, we are quite a small country, 5 million inhabitants. But as you saw, this is also about the North Sea. We also have developments in the Baltic Sea, and this is also very much on the agenda for the European Commission. So they also have an energy system integration strategy where we can look at the long-term planning towards the 2030 and 2050 and see how we can develop from single energy systems to a more integrated energy system. But it is complex, it needs planning, and at the same time, we don't really have all the technologies yet, so they also have to be developed at the same time. And but we see a large interest in these areas and also large interest in investment. So I think the only thing we don't have that is a challenge with finding the investors here, because there is a large interest if we have the right projects. So this were my insight in the European experience. Not much time to tell about all the things that are going on, so I can just recommend to look at some of the things going on in other conferences, and you're also very welcome to contact me. Thank you.
Thank all three of our speakers, Michael and Hannes. Thank you very much. And we've got questions for all of you. And the question with the most thumbs up, the most votes, is a question that I think probably best belongs with Michael, and it is the following. The ISO FERC approved tariff does not accommodate the planned approach. What has to change for the ISO to adopt a fully integrated resource planning approach?
Yeah, so this is interesting. I think there's an intersection between states, the RTO, stakeholder processes, and FERC to kind of come together and drive the political will to change the planning and cost allocation policies at the RTO level. And this is what we saw. This was kind of what led to success in MISO, for example, where basically the interconnection queue for wind had become just unbearable. The backlog was centuries at one point about 10 years ago, and the states came together and said, okay, we have to do something different. We can't keep going through this interconnection queue process and use that to build out the network. We need to do a proactive multi-value planning approach and then broadly allocate the cost of that transmission by building a portfolio of projects across the entire footprint. And so it was kind of the states, through PUCs and their governors kind of coming together, putting pressure on MISO through the organization of MISO states. And then also, I think you had a supportive FERC kind of at the top-down level, also seeing this problem and pushing the regions to come up with solutions that would work. And I think some of the other questions was, do we need legislation to do this? No, but it could help. FERC has existing planning and cost allocation authority under the Federal Power Act to basically do everything that needs to be done. It's just a question of political will. And having legislation from Congress directing FERC to do this, to do the right planning and cost allocation approaches, I think would also help. But I think probably even more important is at the state level, kind of mobilizing governors, mobilizing the PUCs, and at the RTO levels, having in the stakeholder process, the changes kind of working their way up through that. At the same time, you've got the federal pressure from the top. I think that's the winning solution.
Thanks, Michael. We're going to go again with the second most votes, and here's a question. What do you think about the possibility of having an offshore RTO encompassing all the East Coast wind energy areas? Michael, you may be the best person to answer this.
Yes, this has been a popular question. We've been debating this with others. I don't think it's the ideal. You want to minimize seams between RTOs, and you've already, as I mentioned, this is already a difficult part of the country because you've got a seam between PJM, New York, and New England, where most of the lease area is, and that just complicates the transition planning and cost allocation, as well as there's market inefficiencies at those seams. So it's not ideal to have another RTO. However, I think there is value in, as I mentioned, a lot of what needs to be done is kind of pushing the RTOs, the existing RTOs, to do the right thing. And RTOs respond to competition and threats of, people leaving to go join a new RTO probably more than anything else. And so, there might be some, if existing RTOs are failing to make the necessary reforms to the planning and cost allocation policies, this idea could have merit to kind of light a fire under them and make them, have more pressure to move in the right direction. But I think it's not ideal. I'd rather see the existing RTOs work within their stakeholder processes and do what needs to be done with the planning and cost allocation.
All right. Keep voting, everybody, because the order of questions is changing based on that. Here is a question for Peter. How big a role will green hydrogen have for sector coupling and offshore wind? How big of a role?
Yeah, I think in future we'll have quite a large role. What we see today is that there is around 20 gigawatt of offshore wind to an area that you can compare with the US East Coast when you look at electricity consumption. So you can say the first 20 gigawatt of offshore works fine, can integrate it in the system. But what you see now that tenders, public tenders on new offshore wind is together with hydrogen or some kind of consumption of the electricity. So I think for the next 20 gigawatt, it is necessary. Otherwise, we cannot integrate the electricity. But also we need the hydrogen to reduce CO2 emissions in other sectors where it may not be so easy just to electrificate.
Excellent, thank you. Next question is for Hannes. The planned transmission approach sounds like a no-brainer for large-scale offshore wind integration. What prevents its implementation, if anything?
Well, really good question. I think the implementation will ultimately have to happen because it's the only way to get it done. It's only a question of how quickly it will happen. And I think the main reason why it's not happening already, you can do planning before you actually construct it. Planning would be really helpful to know what the answers are, what the true cost advantages are. And I think the barrier to planning is at the RTO level. Michael answered this already, that actually there is no prohibition in the ISO tariff to not start planning or not have started planning years ago. The ISOs can do the planning, and if the states are willing to cover the costs, these plans can be implemented under the existing tariffs. I think what holds us back is the states are eager to get the first few projects done, so they don't want to delay project implementation through a planning process that might take several years. But I also think in New England specifically, it's a lack of leadership by the ISOs to not get that done. In New England and PJM, the ISOs are sort of waiting for the states to come to them with specific requests, and the states haven't been organized enough and don't really have the expertise for that. In New York, it's quite the opposite, where New York and ISO have been, the state and the ISO has been working closely together. It's easier in a single state RTO. And planning processes are underway. And later this year, we see the first results of some of these initial planning efforts and what comes out of them. So I think it's a leadership and vision
About a week ago, the governors of all but one of the states in New England ISO did sign a vision statement, right, asking the New England ISO to modernize the grid, and specifically made comments about transmission for offshore wind, I believe. Do you see that as a step in the right direction?
Absolutely. That's absolutely a step in the right direction. At the technical conference, however, we also got the sense that the ISO was a little bit defensive about that, saying, well, we're doing a lot of generation interconnection studies and a lot is happening. So we'll see how far that gets us, but I think it was a very helpful and very strong first step by the governors.
Next question. Thank you, Hannes. Thank you very much. Next question goes to Michael. It seems cheaper just to retrofit the existing natural gas combined cycle plants with carbon capture sequestration rather than to socialize all the transmission costs for offshore wind. Has anybody studied the economics?
I think the short answer is no, but I'd take a few issues with some of the parts of that question. First of all, I think what we're talking about here is trying to minimize the cost of this transmission and have it provide the greatest value. We're building this offshore wind under state mandates regardless. We're going to be interconnected. It has to be interconnected somehow. And the question is just, can we do that in a more efficient way than we are currently? And so ultimately, all of the cost is going to flow through to ratepayers, whether it's under the current process, the cost of the transmission is rolled in with the cost of the generation, and that goes to the ratepayers. If we're kind of the more preferred approach of the broad cost allocation with the kind of a proactive regional planning process, the cost is still going to flow to the ratepayers. We're just going to hopefully reduce that cost because we're going to do a better job of planning the transmission, and we're going to design it in a way that it can maximize other benefits of that transmission. And I think that's the key piece here. When we've seen with the MVPs and with other, the SPP analysis that they've done, kind of retrospectively looking at the upgrades they've done. If you plan transmission well, you get benefit to cost ratios 2 to 3 to 1. So it pays for itself by solving market efficiency problems, doing reliability benefits and other things. So I think it's this question of, can we do this more efficiently than we're going to? Right? And that, I think, will benefit ratepayers. I'm less of an expert in carbon capture. I think the economics are a big challenge still. Maybe with very high carbon prices, you can maybe start to make it work. But many of the plants that have gone forward to date have not been successful. Even Petronova, the one that is held out as kind of, and this is for coal capture, been held out as kind of the success story, was shut down just because it's not economic. You have a lot of parasitic loads with the carbon capture process, recycling and stuff like that, and I think it'd be very challenging to make the economics of that work, particularly in a region where the pipelines are already constrained, and you'd have to burn more gas to kind of power the carbon capture, and the region is having trouble getting enough gas during certain periods. So I haven't done the analysis, but I think transmission is, if you do it right, it pays for itself.
Excellent. Okay. Next question. This is for Hannes. Hannes, do you have any idea of the scope of upgrades required for the 30 to 40 gigawatts of offshore wind in the Northeast?
Yep. It's probably going to be about $15 to $25 billion in onshore transmission upgrades based on the typical cost of large-scale transmission overlays. So that's going to be a real challenge just from a constructability, permittability perspective. But one thing is clear, the only way to get beyond the first few thousand megawatts of offshore wind is to plan for it. And that planning has to figure out the likelihood of actually permitting the transmission infrastructure that is needed.
We'll do one last question because it's important. For Hannes, with a planned approach, do you think it's possible to reach the rate of deployment required to meet climate goals?
That's the only way to possibly reach it. So will it be enough to reach it? Yes. I mean, I definitely think technology and technology costs have evolved to the point where this can definitely be feasible. And there are studies showing that one can do that without necessarily increasing customer costs on a net basis. but it does require careful planning. And the sooner we start that, the better, because this is not an exercise where we plan for 6 months and then know the answer. This is a multi-year process, and we have to get this started now.
Thank you, Hannes. I want to thank all the speakers, and I'm going to ask Sarah Courtney if she would like to wrap this up.
Thanks a lot, Melinda. Great job managing the questions, and thank you to all the participants for their really compelling questions. I think we got a really good sense of the state of play in the offshore wind transmission discussion in this country, and we'll look forward to watching the work of all these panelists contribute to that discussion going forward. I'd like to remind everyone that there are 2 more technical sessions that will be held as part of the ESIG Fall Technical Workshop Series, both in the 2nd week of November. You can find the schedule for the remaining sessions on the ESIG website, and you're all invited to attend. The next session is on advances in systems, operation, and market design, and this is on Tuesday, November 10th at 2 p.m. Eastern. Thanks again for all your participation. Stay safe and have a happy Halloween.